Hello, my name is Pasha Sadegian. This presentation is for the Internet Technology and Security Transactions, ICI TST 2017. I will present to you our work titled Assessment of Fuzzy Min-Max Neural Networks for Classification Task. A little bit about me. I hold an MS in Computer and Information Sciences from the College of Charleston. I have included my email in this slide. Please feel free to contact me if you wish to do so. This is the agenda for our presentation today. First, we will discuss how statistical distributions are classified today. Then I will present to you some related work, followed by our approach, which is using neural networks and fuzzy logic. Then we will dig a little bit deeper into our classifier, the classifier that we use for this study, the fuzzy min-max neural network, and then followed by our results and some recommendations for future work. Generally speaking, if you use specific classifiers designed for specific statistical distributions, you can expect great results. Other researchers have used other machine learning tools, for example, the fuzzy Gaussian naive Bayes classifier for the classification of statistical distributions. The possibility is also there for you to use different machine learning classifiers for these tasks. In 2015, 4 researchers assessed the performance of the fuzzy Gaussian naive Bayes classifier for the classification of 5 different statistical distributions: negative binomial, logistic, log normal, gamma, and Weibull. Our work follows the work of these researchers. In our study, we use the same statistical distributions, and we also use the same parameters. So the parameters that I will present to you later in this presentation were taken from the study done by these researchers. So we have 4 dimensions, and each dimension has 4 classes, and this is repeated for each of the statistical distributions. And you will see those in greater detail later in this presentation. These researchers, they used 40,000 observations for each dimension. We use 10,000, and they also reported their results in terms of kappa coefficient. We report our results in terms of a simple accuracy rate, a simple success rate for the classifier in correctly classifying the different classes within a certain dimension for each statistical distribution. You can think of the kappa coefficient as the accuracy. The two are not the same, and these researchers, they do go into great detail on how to actually calculate the kappa coefficient in their paper. In 2014, the same researchers used the fuzzy Gaussian naive Bayes classifier to classify 6 different statistical distributions. The distributions included binomial, continuous and discrete uniform, exponential, Gaussian, and Poisson. In our approach, we use 2 different classifiers. One is the fuzzy min-max neural network, which was introduced by Patrick Simpson in 1992. And the other classifier used in our study is the enhanced fuzzy min-max neural network introduced by Mohammed and Lim in 2015. The original model in 1992, many iterations of it have been introduced over the years. Some of them you can see on the slide, but they do include more iterations of the original model. But our focus will be on the original and the most recent versions. So looking at the fuzzy min-max neural network, this is a three-step model. It has a hyperbox expansion phase. The expansion phase is followed by an overlap test, which we will cover in the next slide. And that is followed by the contraction phase. So when presented with new data, you start with the input nodes, the input layer, and the class nodes layer. And through the expansion phase, the algorithm generates hyperboxes. The number of input nodes is equal to the number of features that you have. So if you have 3 features, you have 3 input nodes, and if you have 4 features, you have 4 input nodes. You can see an example of a hyperbox, a 2-dimensional and a 3-dimensional hyperbox. And the number of dimensions of the hyperbox is equal to the number of nodes in the input nodes layer, which is equal to the number of features that you have. So in our case, in this research, we had one dimension. So our hyperboxes were simple one-dimensional hyperboxes with a min point and a max point. So our hyperboxes were similar to a line, essentially. What's important to note about hyperboxes is that each hyperbox, no matter the number of dimensions, can be described by 2 points: the min point, which is usually denoted by V, and the max point, which is typically denoted by W. And that's true if you have a 3-dimensional hyperbox or a 10-dimensional hyperbox. The expansion phase is controlled by a parameter called theta, or hyperbox expansion coefficient. So the larger theta, the larger your hyperboxes can be. Omega, which is another parameter when using the fuzzy min-max neural network, or the enhanced version. This is true for both iterations of the model. Omega is used during the testing phase, where you're trying to associate an unknown data with a specific hyperbox. And omega is the measure of fuzziness or the sensitivity. In other words, if you have a higher omega, you will be more strict in associating a certain observation, new observation, unknown observation, with this specific hyperbox and then a specific class. So that's the distinction in theta and omega. The hyperbox expansion coefficient is treated differently under the fuzzy min-max neural network and the enhanced fuzzy min-max neural network. You can go into you can read the studies and get a better understanding of the differences, but there are some subtle differences. The two models, the fuzzy min-max neural network and the enhanced fuzzy min-max neural network, also differ in the contraction phase, but the two models are quite similar. Now, regarding the overlap test, this graph provides a good illustration of how the overlap occurs and what happens after the contraction phase. And this is one of the problems with the fuzzy min-max neural network. And the problem is that you can see point B belongs to class 2. But after the contraction phase, because there's an overlap, so the algorithm has to separate out, has to contract the two hyperboxes to avoid overlap. You can see that error is injected into the model, because point B, which we know belonged to class 2, will be classified by the model as belonging to class 1, and this is an error which is presented into the model. The enhanced fuzzy min-max neural network tries to mitigate some of that, but this problem still exists, even in the most recent iteration of the fuzzy min-max neural network. Before I get into the dataset, one important note that I should have mentioned about the fuzzy min-max neural network is that it's an online model. It has an online learning, meaning that the model can learn from new observations in a non-destructive way. In other words, the model does not, when presented with new data, the model does not have to relearn everything that it had learned from scratch. It can simply learn ad hoc or online, which is an important feature of the fuzzy min-max neural network classifier. So a little bit about our data set. As mentioned, we will generate observations for 5 different statistical distributions, which include negative binomial, logistic, log normal, Weibull, and gamma. For each class, we will have we use Monte Carlo simulations to generate 10,000 observations for each class, and 2,500 of those observations were allocated to the training sample, and 7,500 observations were allocated to the test sample. And you can see the parameters that we used for each of the classes within each dimension for each of the statistical distributions. So in our case, each dimension had 40,000 observations. So you can see the parameters used for the negative binomial, logistic, log normal. And you can also see the parameters used for the gamma and Weibull distributions. As noted before, these are the same parameters used by the researchers that we chose to build our work on top of. These are the parameters that we used in our preliminary tests. So we used different sensitivity measures and different measures for the theta coefficient. However, based on our focus, our emphasis on accuracy, we decided to settle on 1 for the gamma or sensitivity, measure of sensitivity, and 0.05 for theta or the hyperbox size. Now, on our results, you can see the results using the fuzzy min-max neural network and the enhanced fuzzy min-max neural network for the negative binomial. We were not able to observe any material difference between the fuzzy min-max neural network and the enhanced fuzzy min-max neural network for any of the statistical distributions, both in terms of accuracy and the average number of hyperboxes. The results that are reported to you are the averages of 10 iterations for each dimension, and each of these iterations were independent, and random numbers were generated independent of one another for each of the iterations for each dimension. You can see that for the negative binomial, our results hovered from 75% to roughly 80% accuracy. You can also see the standard deviation of our accuracy measures. Here you can see our results for the logistic distribution. For logistic, we we recorded the best results among the 5 distributions that we studied in our study, and the accuracy rates for logistic hovered from 95 or 96% to 98% accuracy, which was very high. You can also see that the standard deviation of the accuracies were very low. Here you can see our results for the log normal distribution. For the log normal, our results hovered from 85% accuracy to 90% accuracy. And our standard deviation for our accuracy measures was still quite low. This slide you can see our results for the gamma distribution. Again, our accuracy is ranging from 85% to 96-97% accuracy, with the standard deviations of the accuracy measures being quite low. And you can see the results for the Weibull distribution. And here the results hovered between 75% to 86% accuracy. Based on our results, we can strongly recommend the fuzzy min-max neural network for the classification of logistic distributions, because that's where we got a very high accuracy rates. We can also strongly recommend the classifiers, our classifiers, for the log normal distribution. Now, aside from the logistic and log normal distributions, we did get decent results for the negative binomial and Weibull distributions. Anything above, we believe anything above 70-75% accuracy is a strong indication that the classifier is capable of classifying the distribution. We can also recommend the model for gamma, for the gamma distribution, but not as strongly as we would recommend the fuzzy min-max neural network for the classification of the logistic and log normal distributions. For future work, we recommend the following. One is to find the optimal theta and omega in terms of time efficiency and space efficiency, but also in terms of accuracy for different statistical distributions. The other area that we believe there is room for research is using different statistical distributions, so using the fuzzy min-max neural network and the enhanced fuzzy min-max neural network for classifying different statistical distributions, different from the ones that we studied in this paper. And finally, we think there is room for research in using different machine learning models and classifiers for classifying statistical distributions. This brings this presentation to a conclusion, and I appreciate your attention, and we are open to questions. Thank you.